Hello everybody and welcome to our next chapter, Physics Chapter 3. And in this chapter we are covering thermodynamics. So the first important thing about this chapter are the laws of thermodynamics. So the zeroth law of thermodynamics states that when two systems have the same average kinetic energy, they will have the same temperature, which means no heat will be transferred. But until that point, one system is always going to be giving heat off and the other system is always going to be receiving heat until they reach thermal equilibrium. The second law of the first law of thermodynamics is that the total energy of the universe does not go up or down. And this is also an important equation. So delta U equals Q minus W. So that is saying that the change of energy in the delta U is the change in the system's internal energy equals the energy transferred into the system as heat minus the work minus work. All right, and so if we go down here, the Q values and the W values are important. So positive Q value means heat is added to the system. A negative Q value means that heat left the system. A positive W value means that the system did positive work, and then a negative W value is the system does negative work. So another and last law of thermodynamics is the second law, and it states that in a closed system, energy will spontaneously spread out. And we even also know that is entropy, and we show it over here a little bit. So high entropy means more disorder. It means, as a gas, for example, has more entropy compared to a solid where the particles are not as spread out. So it's just the amount of spreaded outness that the particle has. So that is entropy, and that is what we see in the second law of thermodynamics. Same thing. If you have like food coloring, for example, in water, you drop one drop of food coloring in the water, it doesn't just stay in that one place. It like disperses and diffuses in throughout the rest of the water, and that's what happens, with gases and of that nature. So that's when we're talking about entropy. Another thing to note is thermal expansion. So sometimes when things, are heated, they expand. We see that. That's why our sidewalks has cracks. So that they can expand without cracking. And so there can be a change in length or a change in volume. So the change in length is alpha times alpha L delta T, and the change in volume will be beta times volume delta T. And so some of those constants will be given in the question. So let's move on to our types of heat transfer. So there is conduction, which is when two solids are in contact. Then we have convection, and that is the circulation of fluids. And then we have radiation, which is the emission or absorption of electromagnetic energy. Okay, and that we also have types of systems. So we have an isolated system that does not exchange energy or matter with its surroundings. We have a closed system that exchanges energy but not matter with its surroundings. And then we have an open system that exchanges both energy and matter with its surroundings. And this brings us into our state functions and our process functions. So our state functions, for example, enthalpy, density, those kind of things are pathway independent. Okay, but stuff like heat and work are process functions, and they are pathway dependent. So it's kind of like the displacement versus distance. Those are kind of a way to look at it. Instead, if you're going from here to the top of the mountain, the pathway independent is saying, okay, what is your displacement from the top to the bottom? Okay, that would be your pathway independent things. And then the pathway dependent, for example, would take into account the whole pathway that you take to get up to the top. So those are our two kinds of pathways that we're kind of dealing with. And then we have our processes with constant variables. I'm hoping you can see the graph over here. Move it a little closer. There's a light glaring, so I'll have to turn it sideways. All right.